I want to do is, I want to talk about how do you use MATLAB for automated PID tuning, and then how do you use those values and input that into your program. Afterwards, I would like to actually show you a demo of a simple system and then show you how the PIDs work with the actual system. Then, if possible, I don't know if I have time today, I would like to take some test cases wherein I would like to take a robotic vehicle or a robot car and then show you how PID can be used for tracking, how can PID be used for line following, how PID can be used for pursuit type of algorithms, and then kind of go to the quadcopter or omni vehicle, which means you have mechanism wheels and it can go in any direction. So I would like to take some test examples that will make your understanding of PID very clear. But please understand, first, let me answer the question that I started talking about in last class. If you have MATLAB, this would be a good time to start MATLAB. So, online students, can you see my screen?
Yes.
Okay. Now, what I want to do is, how do you tune PIDs interactively? In last class, we talked about a spring mass damper system. We talked about a spring mass damper system. And can someone tell me the values of the mass? What was the mass? Do you remember? 110, 1 kilogram. What was the stiffness? K, 20 Newton per meter. And what was the damping? 10. So the transfer function for this guy, the transfer function for this guy was 1 divided by S square plus 10S plus 20. This was the transfer function. And then we tried to design the PID control. So now what I want you to do is, we are going to do the same experiment, but inside the MATLAB. So first, I would say TF is equal to, so S. So just a second, let me open my. So S is equal to TFS. And then what I want to do is, I want to create the transfer function TF is equal to 1 divided by S square plus 10 times S plus 20. And next line is PID TUNER TF. So these are the commands that I want you to enter. And after this, select this and run. So I made a mistake. This should be small s, not capital S. And it will open the PID tuner. It will take some time and then it will open PID tuner. Now in PID tuner, what you can see is you can design different types of controllers. So you can design just proportional control. You can design proportional plus derivative control, or you can design proportional plus derivative and integral control. Now, if you look at the PID tuner, once you click on the controller, can you see by default, there is this PI controller that is selected. If you want to see the parameters, just click on the parameters and it will show you the parameters of KP. It will show you the parameters of KD, no, KI. And as you can see, KD is not used. And then it will show you the performance specifications, the settling time, overshoot, peak, gain margin, and phase margin. Yeah.
Could you go back to the code for a second?
Yeah.
Do you have S defined in your workspace somewhere? Yeah.
What?
It's giving us an error using the TF function when we're trying to pass the S.
Did you STFS?
Yeah, that first line of code,
Yeah.
it's like giving an error.
Oh,
Do you have that defined somewhere?
no. Basically, probably you don't have the control system toolbox then. What about others? So you need to install the control system toolbox. So you don't have the PID tuner. So now what this is this is reference tracking, which means we gave it a step input and this is how the system is responding. And as you can see, the system is responding quite okay, which means the output, this is the tuned response. You can actually play with these parameters. You can actually select a different plant. You can actually add a plot. For example, if you want to do open loop, as you can see, this is the open loop response. And you can see this is the closed loop or the tuned response. One thing I want to talk about here is the important parameters that they talk about is something called as the phase margin and gain margin. These two are important parameters. Now, if you talk to a control systems guy, they will spend lectures and lectures talking about the phase margin and the gain margin. Let me tell you what these two parameters mean. System would become unstable as soon as the eigenvalue cross the imaginary axis. And I spent a lot of time talking about it. So I want you to understand. So this is the S plane, wherein you have eigenvalues. Eigenvalues will have a real part and eigenvalues will have an imaginary part. Alpha plus beta I. This is the imaginary axis and this is the real axis. As long as we are here, the eigenvalues will have negative real part. You agree with me? This is, so eigenvalues will have, this is 0, 0. Eigenvalues have negative real part. As soon as you are on the imaginary axis, eigenvalues will have 0 real part. Do you agree with me? As soon as you cross the imaginary axis, eigenvalues will have positive real parts. Everyone understood this? That is the only thing that you have to remember. Linear system stability is dictated by the eigenvalues of the system. If eigenvalues are the poles of the transfer function, the poles of the transfer function means when the transfer function becomes 1 over 0 or becomes 1 divided by 1 divided by 0 becomes infinity. So eigenvalues As long as they are on the left-hand side of imaginary plane, things are fantastic. As soon as they are on the imaginary axis, things are okay, but not bad. But as soon as they cross the imaginary axis, the system becomes unstable. Everyone understood this? Now, this gain margin and phase margin, both of these concepts relate to how far eigenvalues are from the imaginary axis. The classic definition of gain margin is the amount of gain that you can add into the system till system becomes unstable. The phase margin is amount of phase you can add to the system till system becomes unstable. What essentially it means is if your gain margin is small, that means you are close to the imaginary axis. If your phase margin is small, again, that means you are close to the imaginary axis. So farther you are, your gain margin is higher, your phase margin is higher. This is not the exact strict definition of gain margin and phase margin, but I want you to understand gain margin and phase margin indicates how much of stability margin that you have. As soon as you cross this imaginary axis, you become unstable. So how much stability the system has? MATLAB uses its own built-in algorithm to add 60 degree of phase margin to design the controllers. So MATLAB uses its own internal algorithm to add 60 degrees phase margin and finds out the PID gains. As you can see, for the system, we have implemented the KP value as 34, KI value as 96, and there is no derivative term. Everyone understood this? Now, you may ask me, okay, all this is great. Then how do I use MATLAB to design a PID control for my actual robot? Here is what you do. You develop the mathematical model for the robot. For example, the mathematical model would come from Euler-Lagrange. Then what you do is you linearize the model. Linearize means find a linear approximation that gives you equivalent results. Please try to understand. All the robotic systems are going to be non-linear. So they are never going to be linear. But what you can do is you can take a small segment of that non-linearity and approximate that by a straight line. That is what is called linearization. So you may have a non-linear robot, but the segments of that non-linear robot would be linear. Everyone understood this? As soon as you have a linear approximation, you can find a transfer function. Do you agree with me? And as soon as you find the transfer function, you can design the PID gains. What it means, and this is very important, and this is a very fundamental concept in controls. You have a nonlinear system, you convert that into a segmented, linearized system. What does it mean? Which means the transfer function when the nonlinear system is operating within this particular operating range is different than the nonlinear system is operating in some other operating range. So which means you have a transfer function, you have a different transfer function, you have a different transfer function, but all these transfer functions together give you a fairly decent, not exact, fairly decent approximation of that nonlinear robot. Everyone understood this? And for each segment, you design the PID control and schedule the gains. That is the basic principle of gain scheduling, which means you have different PID gains and different models depending upon where the robot is operating. So you know if the robot velocity or speed or angular displacement is within certain range. As soon as your sensors tell you that robot is in this range, you would use that particular transfer function, that particular PID, and control the robot. So basically, you schedule the gains. That is what is gain scheduling, and that is very commonly used in industry. Yeah.
When we linearize a non-linear function, we are taking a very small part of a non-linear equation, right? So, like, will there be like infinite number of step PIDs?
No, basically what they do is you look at the nonlinear behavior of the system. And to be honest with you, that is not done by hand. There are MATLAB functions that will find the linear approximation, or also called as trimming. So they will find, and we do this all the time in the terms of aerial robotics. All aerial robots are nonlinear. So what we do is we trim or we linearize the aerial robot about the operating point, and that linearized system is continuously controlled using the PIDs. And then the problem is there is a concept which is called as successive loop closures. For an example, on the robot you will have an innermost loop that is controlling certain part of the robot. Then you will have an outer loop, and then gradually those loops go on becoming bigger and bigger, and overall system gets controlled. But at the end, if you want to use the PID, you have a nonlinear system, you find the linearized approximation, find the transfer function, and then actually use the PID control, and it will give you good results. Yeah.
So if there is a highly non-linear trajectory that my drone has to follow.
If yeah, then if it's a, so for an example, if your drone is doing flips, or if you are doing drones something like 3D acrobatic, then perhaps PID is not the good way to do it, but you have to use some type of nonlinear control. And there are certain cases when you have to use nonlinear control, but we'll talk about it more in detail. But when we study some concepts in robotics too. But right now, what I want you to understand is, with this tool, why is phase measured in degrees? Because what does the phase mean? Phase means if you have a system, you supply an input, the output is going to lag the input. Output will never, unless it's a zeroth order system, then the output will coincide with input. If it's a first order, or if it's a second order system, then the output would lag the input. I give you an example. You have a thermometer. You dip the thermometer in a pot of boiling water. There is some time constant before that mercury expands and reaches the steady state value. So that time constant means the output is delayed with respect to the input. So think about it like if you were to feed a sinusoidal input, the output would be sinusoidal, but output will be delayed. And that is what is meant by phase, the degree separation between the input and output. So that's why it is measured in terms of degrees. The other thing which I want to show you is this particular tool allows you to control different types of controllers, and I would encourage you strongly to play with this. So 1 degree of PID control, PD, PID, PI, these types of controls can be implemented, and then depending upon what is your requirement specifications. For an example, you can say you want your system to be super responsive, then you can actually change, actually move these tabs and then design the gains. This whole thing can be done inside the Simulink as well, but I want you to be aware of this PID tuner. And clearly, there is an excellent webinar on using PID tuner, and I think it is part of your assignment 6 or 7. I think there is a control systems webinar. I would strongly encourage you to take a look at that seminar or webinar that will actually make you more familiar with this. If you want to do the analysis in frequency domain, you can do it. If you want to do the analysis in time domain, you can do it. Any questions here?
For linearization, do we use something like a Fourier transform?
You can do linearization in lot of ways. So linearization is just finding a linear model of a nonlinear system. So you can use a numerical linearization, use an analytical linearization. You can actually use some type of Padé or approximants, and then you can find the linearization. But linearization, if you want to do it, I would actually, we will do a lot of linearization when we study robotics too, because the quadcopters, as a matter of fact, fixed wing vehicles, they are nonlinear systems. So basically, the way we have found out the equations of motion, we take those inside the MATLAB and use numerical approximation solvers to linearize the system. Now, with this, the theory part of the PID I have finished. But now what I want to do is I want to show you some practical demos of PID. And I'm going to show you this practical demo with using one tool, which is TC Lab. So and this is a fantastic tool to learn dynamics and control. You can actually teach machine learning, data analysis with this. You can design all the exotic linear, non-linear, model adaptive, different types of controllers. But I want to use this just to showcase the PIDs and how PIDs affect the performance of a system. So what this is a simple system wherein you have a heater element and you have a thermistor. So basically you have a heater, that is your actuator, and then you have a thermistor that measures the temperature. And the idea is I want to make sure that the temperature remains at a certain set point. So there are different types of controls you can use. You can use a bang bang or on off type of control. You can use a PID type of control, and you can use some exotic nonlinear controls or adaptive controls, or you can use machine learning, etc., etc. But what I want to show you here is this is the layout of this apparatus. So you have an Arduino Leonardo, which is at the back, that is used to control and measure the temperature. You have the heaters, heater 1 and 2. So you can do single input, single output, or multi-input, multi-output. So you can do single input, single output, or multi-input, multi-output. You also have the temperature sensors that will measure the temperature, and you can implement system modeling. Again, first order with dead time, that is FOPDT. That is a very classic model that is used to model temperature effects. But we are not going to look at the modeling. We are going to look at just simple PID. So this is the system. What I'm going to do is I'm going to connect this system, and then I will run the Simulink file, and then we will see how the system behaves with different PID controller gains. Because we have looked at the PID behavior in simulation. We know simulations work, but now what I want to do is I would like to show you the actual effect of PID controller gains on an actual control system. Let me tell you, if you have done the robot control lab, either the rover or the balancing bike, you have had good experience of PID tuning and PID control. But if you have not had any experience, I want you to understand what is going on, because PIDs, in theory, it's all great, but you have to see them working in actual practice. So what I'm going to do is, I'm going to go to, first, we are going to study the open loop response. So this is the Simulink file for the open loop response. Let's open it up. Let's look at the open loop response. Okay. The system is set up. Let's see if it is. If it will compile. So this is the Simulink file. And what I want to do is, for the first time, it needs to compile the code. So in case online students are wondering what's happening, is I have connected this TC lab to the USB, and then I would be performing the PID control experiment. This in MATLAB, it's not working. Let me restart. Just bear with me for a second. Okay. Now I'm going to run this. So this is the temperature control lab. This is the Simulink block. The set point is at 40 degrees. And I'm running this system in an open loop. So I have this heater that is providing the signal. This is for time syncing, and this is sending the output. So right now, once I run this, you will notice this is the behavior of the system in open loop. There is no feedback. So the system is running in the open loop. So the way it works is you send the input. As you can see, that blue line is the set point. I want my temperature to be at 40 degrees. I know the count to voltage ratio, which means I know at what voltage, what is the temperature that heater is supposed to be at, and I'm going to supply that those number or those many counts onto the heater element, so that with a hope that my heater would go to the temperature of 40 degrees. And you will see that set point is at 40 degrees, but this system is running in an open loop. Can you see there is no feedback? Just you have a set point, which is blue, and then you have the output of the system. Are you with me so far? You will also observe that it will take a lot of time for system to go to the set point, and that system would kind of oscillate back and forth. And then I will show you what happens if there is a disturbance. So for an example, I don't know if you can see this. This has become a sort of pink. Yeah, pink. That is indicating that this heater is hot, and this hot light is also turned on. So it is an indication that this glue is now hot. So it will gradually, yeah, and then the hot light will also come on. So in case the students, you can see that this has turned pink and this light is turned on, which means indicating that the heater is hot. Yeah, the glue, thermal glue. So thermal glue turns into pink when it gets hot. So it's just like a safety measure. It gives you a visual indication. Hey, don't touch that heater. That heater is hot. Now you can see that it's going, and it's actually exceeded. It's kind of oscillating. Now I want you to see, if I blow on this, that is an external disturbance. It won't be able to catch up. So you will see that there is a disturbance. If you want to see what I'm doing, I'm blowing on this heater, and you will see that the open loop system is not able to respond to the external disturbances. Oh, can you show again? Okay, this is the system. I'm gonna blow on this heater, and as you can see, the open loop system is not able to respond to the disturbances. Any question related to this demonstration? Now I'm gonna stop this, and then I'm gonna open the Arduino PID. So which is open loop. Arduino PID SLX. So this is the Simulink file, wherein now please observe that what I have is I have the temperature, and I'm getting the feedback from the temperature feeding that into the summing junction, and I'm feeding that to the PID control. And this PID gains, how would you set these gains? I'll tell you. The way you do it is, and it's actually a very nice experiment that I hope that you'll at least watch that on apmonitor.com. What you do is you collect the data from the heater, get the relationship between the input and output, and find out whether the first order model, second order model, or zeroth order model gives you a good fit. So you do a system identification based on the data. Then use that system identified model to design the PID controls, and then use those PID gains for actual control. It works beautifully. And this is exactly how the systems are controlled in the actual practice. Many a times the mathematical models, what we do, they are mere approximations of the systems that are built. So once the system is built, what you do is you run some experiments, get data, construct the model based on that data, and then use that model to find out the PID gains, and then use those PID gains for controlling the system. So at the end, you will notice the model is the first order model. So simple proportional and integral control works. So now what I will do is I will do the exact same thing. This is the closed loop response. And I will also show you something called as the controller effort that we don't usually pay attention to, but that is very important. So let me run this system. So this is the closed loop system wherein you have the PID controller that is controlling this system. It's going to take some time, but what I want to do is, in the meanwhile, I want you to go to my ASU canvas. Go on to canvas, and I have already uploaded some interesting, so go to canvas shell and download the latest and greatest MATLAB files that I have uploaded. So if you go to the canvas, you will notice that there is an RCV copy zip folder. Please download that folder and expand it inside your MATLAB environment, because next few demonstrations, I'm going to use that model. So, oh, MATLAB crashed. Interesting. So next part is I want to do the demonstrations with the vehicle models. So yeah, PID control. Let me show you. Yes, RVC2 copy. That is the zip folder. Expand that folder, and there is a MATLAB script that you need to run. So if you go to downloads, you would see RVC2 copy. Can you locate that in Canvas? Download, expand. Once you expand, you will have this folder. Go to RVC tools, and there is this startup RVC. Just run this. This will actually install all the models that we need for the next demonstration. And let me show you this demonstration of PID. And here is the temperature plot, and here is the control effort. So as you can see, blue line So here yellow line is the set point and red line is actually the temperature. So you will see that red line is trying to track the control. So set point is 40, but now I have this PID control, and that PID control is varying the controller effort. Now, let me specify. So look here, you have this temperature, you have the set point. As you can see, you have the set point. You have the controller input, which is coming after PID, and then you have the final temperature. So now you can see that the actual temperature is kind of tracking the set point. And on the left hand side here, this is the controller, the error. As you can see, this talks about the error. This is the error between the output and the input. My set point is at 40 degrees. But as you can see that my actual temperature is about 42 degrees. So I have an error of about 3 to 4 degrees. Gradually that error will go to 0. As you can see, the error will go to 0. And the actual temperature here will go to 40 degrees. So, and I will give you a moment. Let me explain it to you. Set point is 40. That set point gets fed into the summing junction. Summing junction is tapping into the output, the actual temperature. The difference between the set point and the actual temperature is the error. That error gets fed to the PID block, and I'm displaying that error in this scope. Are you with me so far? So if I click on this scope, you can see this is the error between the set point and the actual temperature. If my error is 0, which means my output temperature is equal to my set point. My error could be positive or my error could be negative. That error gets fed into this PID block, and this PID is going to take either the error, integration of the error, multiply with those respective constants, and feed that to the heater control signal. And then that control signal will control the system. So now you can see that this red line is the actual output, and that is tracking the set point, which is shown by that yellow line quite closely. Are you with me so far? Now I will try to create the same disturbance. I'm going to try to create the disturbance. And you will see that with PID control, the recovery from disturbance is much quicker. Are you with me so far? Yeah. This file?
Where is located inside the RCV?
Oh, yeah. This has nothing to do with RCV, robotics and control vehicle. This is just this demonstration. RCV part is coming. Don't wait for it. There are few concepts that I need to discuss before I jump into that. Okay. I wanted to show you this demonstration because PID control is not a spectator sport. Unless you play with the PID, then only you will realize the power of PID controls. At this point, let me ask in-person students and online students, any doubts, questions about the PID or anything else? Yeah.
How do we decide when to choose PI, when to choose PD?
Okay. So there are actually guidelines and rule of thumb. So the way you typically design a PID, it first and foremost, you design a proportional gain. With a proportional gain, as you can see, we will get quick response. But the problem with proportional gain is we are going to get an overshoot. Okay. And then no matter how much proportional gain you add, you cannot eliminate the steady state error. Do you agree with me? Now, once you see that overshoot, what do we do to minimize the overshoot? Add the D. So next thing is to add D. Then you will see that that overshoot will come down. But the problem with D is D will not eliminate. Sometimes it will actually make life worse in terms of steady state error. So you will still have a steady state error, but now you will have response. And then finally, you fine tune the value of I so that that steady state error goes to 0. But once you start adding I, you will see there might be some overshoot or some sluggishness in the response. At that time, you have to adjust just the P control. So this iterative process that you have to follow to tune the PID gains in actual practice. That is how I did it. But if you look at, there are guidelines on how to tune the PID controls. But this actually worked with me. First, control the P, make sure the system overshoot is reasonable. You cannot eliminate overshoot. System will have some overshoot. Steady state error is reasonable. Then add D so that overshoot is decreased and the steady state error is reasonable. And then tune I so that the steady state error is minimized. But when you minimize the steady state error, you will realize that the performance is either sluggish or may not be like what you want. Then tweak, not change, tweak the value of P. And that is how you tune the PID gains. Everyone understood this? Yeah.
Is it possible to use the optimization to optimize to tuning the PID?
Yes, actually, if you look at the control system toolbox, there are optimizer tools. They use the linear optimization tools to control the PID. But the problem here is this: for any optimizer to run, you need an optimization criteria. For example, you have to specify it has to be minimum time. It has to be minimum overshoot. And many a times, you may not be able to find an optimized solution. So if you can go to, actually, if you go to PID control using MATLAB, there is an excellent webinar on PID control using MATLAB, and they talk about all different tools on how to do it. But at the end, when you perform the experiments, it's matter of trial and error. I mean, even though you run MATLAB, the MATLAB is going to give you as good as a result as your model is. If your model is not accurate, the PID controls are not going to be accurate, and you will have to do some real life tuning. Any other questions? Okay. Any questions from my online students? If there are no questions, what I want to do is I want to give you some more demonstration or discussions of PID control. Now, this I would like to do it using simulations using MATLAB. Now, and let me set up the stage for today's class and the next class. Okay. Now, what I'm going to do is I'm going to show you the application of PID control for a ground robot. I will show you the application of the PID control for an omnidirectional ground robot, which means the robot with mechanism wheels, which can go anywhere. And then I will show you the application of PID control for a quadcopter. One thing I want to talk about is, first and foremost, this is an important word, which is called as holonomic constraint. And believe it or not, when I was a graduate student, people used to use this word holonomic constraint, and I thought, oh, what the constraint is this? I don't know. But let me explain you what do I mean by holonomic constraint. Let me explain you what do I mean by non-holonomic constraint, and then I will give you the equation for autonomous ground vehicles. And then we will control our autonomous ground vehicles using PID. So first and foremost, I don't know, have you done this experiment? Have you solved this problem? The problem is something like this. You have this ladder. This ladder is resting against a wall. I mean, this was a very simple problem that I solved when I was an undergraduate student and when I taught statics. You have this ladder. This ladder is leaned against the wall. And then this is end A and this is end B. And the question is, this end A starts skidding towards left by velocity 5 meters per second. Then what would be the velocity of end B? Remember? What?
Actually, we're doing right now vector mechanics.
This problem is not for vector mechanics, my friend. This is EGR 217 statics problem. This is not a vector mechanics problem. Okay, so the way you solve this problem is you start, this is X, this is Y, and no matter what happens, no matter wherever this point A is, this hypotenuse, that length of the ladder is going to remain the same. Do you agree with me? So I can write down this constraint equation, super important. I can write down this constraint equation that everyone knows, x square plus y square is equal to L square. Do you agree with me? This is a constraint equation. It does not tell me the value of x. It does not tell me the value of y, but it tells me the relationship between x and y. And x and y are the displacement parameters. Do you agree with me? These are positions. I can take the derivative of this guy, then 2x times x dot plus 2y times y dot. L is a constant, so this becomes 0. Do you agree with me? Now, with this constraint, again, now it's very easy for me. Please understand, it's very easy for me to find out the velocity of B. If I give you my x is equal to 5, my y is equal to say 4. Okay, this distance is 5, this distance is 4. I can substitute 2 times 5 times x dot 5 plus 2 times y, which is 4 y dot, and equal to 0. I can solve this equation and get the value of y dot. Are you with me so far? Everyone understood this? Simple, right? Why am I discussing this? I'm discussing this because I want you to understand the most important part. This constraint is the constraint on velocity. Do you agree with me? This constraint is the constraint on velocity. I can integrate this constraint and get the constraint on displacement. Do you agree with me? When you have a constraint on the derivative, a single derivative or multiple derivatives, you integrate those and get the constraint on the states. That constraint is called as holonomic constraint. Holonomic constraint, which means integration of derivative, the constraint derivatives, gives you a meaningful constraint in the state variables. Everyone understood this? Now what happens? Imagine a car. Now here is the example of non-holonomic constraint. And remember this, okay? So imagine that we have a car. That car is going in this direction. Car is going in this direction. This is the radius of curvature. And what you have is, you have this velocity v, and then you have, this is the inertial frame, which is x, this is y. So I have this velocity v, and then I have this theta. So velocity in x direction in the inertial frame is v cosine theta. Vy is equal to v sine theta. And then if I want to find out the radius of curvature, then I can find out theta dot is equal to v divided by r, which is, so this is vx, vy, and theta dot. Are you with me? Now I want to ask you this question. The way I have derived constraint over here, and this is an important question, I want you to understand, I can also write a constraint on the derivatives. The constraint on the derivatives, Vx is the derivative. I can write Vx sine theta minus Vy cosine theta is equal to 0. And I will give you a minute to think about if this constraint will always be satisfied for a ground vehicle, as shown over here. If I have a ground vehicle wherein this wheel and this wheel, they are very close to each other, this constraint must be satisfied. What does that mean? It means, check this out. Vx is equal to v cosine theta. I can substitute here. Vy is v sine theta, that I can substitute here. And can you see that on the right hand side, I get 0. Are you with me so far? Understood? This is also constraint. This constraint also includes the derivatives. Can you see the derivative Vx is the derivative of position. Vy is the derivative of position, x in y direction. However, I cannot integrate this constraint and get the relationship between x and y. I will give you a minute to think about it. I cannot integrate this equation and get the relationship between x and y like that. That's why this constraint is a non-holonomic constraint. Everyone understood this? Yeah.
When we simply substitute Vx and Vy over there, what we get is theta is equal to 45. I know it sounds stupid, but
No. Vx cosine theta. We get, when we substitute Vx and Vy over there, we get 0. You are substituting flip. All right. Now here comes the moment of enlightenment. And I want you to understand this very, very carefully. What is the physical interpretation of non-holonomic constraint? Imagine you are riding a bicycle. Imagine you are riding a bicycle and you want to turn. Your bicycle has 2 wheels. Can you turn when you are standing stationary? No. For bicycle to turn, you should be moving. Do you agree with me? That is the physical interpretation of non-holonomic constraint. Non-holonomic constraint means that if you want to turn, you have to be physically moving. You cannot move on the wherever you are. So that is the reason autonomous vehicles are considered, or ground vehicles, they have this non-holonomic constraint. And that's a holonomic constraint, because you can integrate this. If you want to integrate, you can integrate, but you are not gonna get a clean state constraint equation as shown over here. Everyone understood this? So what is non-holonomic constraint? Non-holonomic constraint, which means if you have a ground vehicle, like a bicycle or autonomous car, if you want to turn it, it cannot turn wherever it is. You need to move forward and turn. So basically you have to move forward and turn. If you have an omnidirectional robot with the mecanum wheel, that we'll talk about it, then basically you can actually turn wherever it is. So you need an omnidirectional robot that you can satisfy this is the holonomic constraint. But non-holonomic constraint means if you have a ground vehicle, you cannot turn the ground vehicle without going forward. You have to go forward and turn. You cannot turn wherever you are standing. So please remember this, because this is not explained the way I tried to discuss it over here. The last, at some point you show how to system identification toolbox. So there is a question whether I would show you how to use the system identification toolbox. Unfortunately, not in this class, but if you take my linear algebra class, which is I'm teaching in spring, I'm gonna do data-driven modeling and analysis using linear algebra. So in that class, I will teach you how to do the analysis using this stuff. So I'm gonna stop here because I don't have time. But in next class, I'm gonna work out the examples on ground vehicles, omnidirectional vehicles, and quadcopters before I conclude the discussion on controls. Yeah.
Will we ever use the inverse kinematics designer in MATLAB?
You can use. Yeah, I haven't taught it, but there are excellent webinars on how to use it.